Hi friends, welcome to this session of maths. Today we are going to look at permutations and combinations. So let's start with the most fundamental thing, fundamental counting principle. So let me give you an example. Let's say you're going out with friends for an evening and you have 3 movies to watch, or rather option of watching a movie from 3 movies. You have 4 different restaurants to go to. You can choose any one of them, and you have, let's say, 2 different ways of commuting back home. So in how many different ways can you spend the evening? 3 movies, 4 restaurants, and 2 ways of commuting. So the answer is going to be 3 into 4 into 2, because you can choose, you have 3 options here, 4 options here, and 2 options here, and all these options are independent. No matter which movie you watch, you still have, for every movie you have 4 options. For every of those combinations you have 2 options for commuting. So you will see that whenever you are dealing with independent decisions, you will have to multiply them, and that is exactly the fundamental counting principle. So what it says is, when there are m ways to do one thing and n ways to do another independent thing, so there are 3 ways of watching a movie and 4 ways of having dinner, and they are independent, these decisions are independent, then there are total m into n ways of doing both. So we can just extend it. If you have 3 choices to make, and one choice can be made in m ways, another choice can be made in n ways, third choice can be made in o ways, fourth choice can be made in p ways. So all you have to do is to multiply, and that is, the number of choices you have overall. So this is the fundamental counting principle. Let's look at this one. In how many ways can 10 boys be seated in a row? So let's look at it. We have 10 boys and 10 rows, 10 boys and 10 chairs. So the first boy says, I have 10 chairs to choose from. The second boy says, because there's only 9 chairs now, one chair is already gone, this person has chosen the first chair, so I have 9 chairs to choose from. The third person says, I have 8 chairs to choose from. That way, right? And all these choices are independent. So that means, what are we going to get? We are going to get the total number of ways as multiplication of all these individual number of ways. So that is going to be 10 factorial. Total number of choices is going to be 10 factorial. You can also think from the chairs point of view. Let's say these are chairs and every chair is asked to choose one person. So how many people, how many choices does the first chair have? It has 10 boys to choose from. The second chair has 9 boys to choose from. The third chair has 8 boys to choose from. That way, again you will get 10 factorial. Right? So this is a practical example of fundamental counting principle. Permutations and combinations is an extension of fundamental counting principles. Both are used to find out possible number of arrangements. Both are used to find out possible number of arrangements. So what is the difference between the two? We always hear these terms, permutation and combinations, and both are used to find out number of arrangements. So what exactly is the difference? Permutation is used when order matters, whereas combination is used when order does not matter. For example, when we are talking about arranging children in a row, right? So let's say this is one child, this is another child, this is another child. Arranging children in a row, now this is going to be a different arrangement than this. All these arrangements are different, right? Because which child is sitting where is important. The order is important. So in this kind of situation, in order to find out the total number of arrangements, we'll use permutations. Whereas if we are, let's say, arranging chocolates in a row, all the chocolates are similar. So this chocolate and this arrangement is the same arrangement. Even if now this chocolate could have come here, now this chocolate would have gone here, this chocolate would have come here, you know, still that's the same arrangement, because we are not really bothered about which chocolate is where. The order is not important. So in this kind of situations we'll use combinations. Let's look at the formula for combinations. When r elements need to be chosen from a set of n elements, that means let's say out of 10 people I am choosing a committee of 4 people, and order does not matter. If I am choosing a committee, I am not assigning them any particular order. Either a child is selected or not selected, and there is not any particular order in the 4 children that are selected, right? So in such cases we'll use combinations. The combinations is written like this, NCR. So it is out of n people I am taking 4 people, and and from n people I am taking r people. In this case is 10C4, and the formula is that n factorial divided by n minus r factorial divided by r factorial. So it is here, it is going to be 10 factorial divided by 6 factorial divided by 4. Okay, you will see that NCR is the same as NC n minus r. That means 10C4 is same as 10C6. Why is that going to be? Because 10C4 is going to be 10 factorial by 4 factorial by 6 factorial, and 10C6 is also going to be 10 factorial by 6 factorial by 4 factorial, right? So NCR is equal to NC n minus r. So let's look at this example. In how many ways can 4 children be selected from a group of 6? So it is selected. That means, are we worried about order? We are just selecting. We are not worried about order. So we'll use combinations. So that means we are going to select out of 6 people, combinations of 4 people, 6C4, which is going to be 6 factorial by 2 factorial by 4 factorial. 4 factorial, see 6 factorial can be written as 6 factorial is equal to 6 into 5 into 4 factorial, right? So this 4 factorial will cancel with this. What we get is 6 into 5. You will see that this 4 factorial actually getting cancelled here. 6 into 5 divided by 2 factorial, which is 15. Let's move to permutations. Similar concept. It is just that order is important now. So I am choosing r elements from a set of n elements, and I am putting them in a particular order. Then we are going to use NPR. The formula for NPR is n factorial by n minus r factorial. Right? Now you will see that the formula for NCR was n factorial by n minus r factorial divided by r factorial. And if you compare this, see this part is the same as NPR, right? So NCR is equal to NPR divided by r factorial. That means number of combinations is number of permutations divided by some number. That means number of combinations is going to be less, whereas number of permutation is going to be more, correct? And let's look at it now. If you are talking about combinations, that means let's say I select one particular combination where I am selecting these 3 items. But among these 3 items also, if I am giving importance to order, then all these see, for this one combination wherein order is not important, I am getting these many permutations because now I am giving importance to order, correct? So that means number of permutations is going to be greater than number of combinations, and for every combinations, how many permutations I am going to have? In this case 1 2 3 4 5 6, so I am getting 6 permutations, which actually is how many numbers I am selecting. Here r is equal to 3, I am selecting 3 people, so 6 is 3 factorial, right? So for every combination now I am getting 3 factorial permutations. So that is why number of combinations into r factorial is going to give me the total number of permutations. Okay, let's look at an example. In how many ways can 4 children be selected from a group and made to sit in a row? Now whenever I'm talking about made to sit in a row, I'm worried about the order, right? So I'm going to use permutations. 6 children I'm selecting, out of them I'm selecting 4, so it's going to be 6 p4, which is going to be 6 factorial by 2 factorial, which is going to be 360, right? It was the same problem last time, wherein what we saw was, if I'm only combining 4 children, I'm getting 15 ways. Now among those 15 ways also, every of those 15 ways is going to give me 4 factorial ways of permutations. So now my answer should be 15 into 4 factorial, which is going to be 15 into 4 to 3 into 2 into 1, which will again come out to be 360. Correct? So there are 2 ways of looking at it. Either first you can do the combination part and then multiply by 4 factorial, or you can directly find out the factorial. In fact, mathematically is the same thing. If you apply this formula, it's basically the same thing. NPR, to find out NPR, you first have to calculate NCR and then divide it by, multiply it by R factorial. So this is the same concept I was just talking about. Permutation is nothing but combination multiplied number of times the chosen elements in a combination be arranged in order. So let's look at these examples now. In how many ways can a team of 11 players be selected from a pool of 20 and a batting order be decided if the any of the selected players can bat anywhere? So now I'm worried about the order and I need to select from 20. I'm worried about the order and I need to select 11. So it's going to be 20p11. One way is to directly apply permutations, 20p11, right? The other way is I first select 11 people. Okay, so I do 20c11. Now out of every of these combinations, how many ever combinations I have, I can decide the batting order. That means now I have one combination of 11 people. I am just worried about putting them in order. So that means the first person has 11 choices, the second person has 10 choices, third person has 9 choices, that way. Ultimately, number of choices is 11 factorial. And this is similar to the very first problem we solved. So a number of arrangements for every individual combination is 11 factorial. So we multiply number of combinations into 11 factorial, that is the number of or permutations for every combination, and ultimately what we get is 20p11. Is the same thing. It is a completely different way of looking at these problems, and this approach tends to apply to both permutations and combinations. So that approach is all status factorial divided by same status 1 factorial divided by same status 2 factorial, etc. So let's understand it from an example. Let's look at a simple combination example. In how many ways can 4 children be selected from a group of 6? So it's going to be 6c4, right? Okay, another way to look at it is I maintain this table where in one row I have first child, second child, third child, fourth child, fifth child, sixth child, and in the bottom I have status. Now I am only worried about selected, I am not worried about order. So status is going to be whether a child is selected or not. So let's say I have 4 selected children and 2 non-selected children, right? Correct? So this formula, using this approach, what do I get? All status factorial. How many statuses I have? Individual statuses, 1, 2, 3, 4, 5, 6. So I have 6 factorial statuses divided by status 1. What is status 1? Status 1 is selected. No, how many of them I have? I have 4 such statuses, so I take 4 factorial. How many I have non-selected? I have 2 non-selected. I do 2 factorial. Ultimately what I get is 15, which is the same as C6C4. The same approach also will work if you are worried about ordering. In how many ways can 4 children be selected from a group of 6 and made to sit in a row? Now I am worried about order. So ultimately my picture is going to look like this. child 1, 2, 3, 4, 5, 6. Child 1 sits in chair 1, child 2 in chair 2, child 3 in chair 3, child 4 in chair 4, and child 5 and 6 are not selected. Right? This non-selected part will remain the same. It is just that among the selected, now I am giving an order. Correct? So now let's apply the same formula, all status factorial divided by same status factorial 1 factorial, same status 2 factorial. So all status factorial is all 6 factorial again. How many chair 1 status I have? Now chair 1 and chair 2 will have to keep as different statuses, right? Because we are worried about the order. So chair 1, how many I have? I have 1, so 1 factorial. Chair 2, how many I have? I have only 1, 2 factorial. Chair 3, how many I have? I have only 1. Chair 4, how many I have? I have only 1. Non-selected I have 2, so it's going to be 2 factorial. So ultimately what I get is 6 factorial by 2 factorial, which is 360, which is the same as 6p4, right? So if you find yourself confused about when to use permutations or when to use combinations, you can always follow this approach. What this approach requires is for you to come up with a table and try to understand how many different statuses we have. Okay, if you are worried about order, give every child or every item an individual status, and then just simply apply this formula, all status factorial divided by items with one status, number of items with one status, that factorial, number of items with second status, that factorial. So let's move to the practice problems. There are 8 problems here. Please give them a try. Okay, let's look at the first one. In how many ways can 5 boys and 5 girls be seated in a row? Now this is seating in a row. That means we are worried about permutations. 5 guys, 5 boys and 5 girls. 5 boys and 5 girls. Okay. There is no restriction. That means we are only worried about, we have 10 items, right? 5 boys and 5 girls. We are making them arrange in a row. That means first person is going to have 10 choices, second person is going to have 9 choices, that way. So we are going to end up with 10 factorial. 2 particular boys always sit together. This is interesting. So what we are saying is, we have 5 boys, 1, 2, 3, 4, 5. 5 girls, 1, 2, 3, 4, 5. But these 2 boys always sit together. Correct? So that means if you look at it, how many items we have now? We have 5 girls, these 3 boys, that is 8, and these boys as 1 unit. That means we have only 9 items. We just have to worry about arranging these 9 items. So in how many ways can we do that? We can do that in 9 factorial ways. Correct? But also you will see that each of that 9 factorial ways, we are not considering the specific order of these 2 boys sitting together among themselves, right? So it could be B1, B2, boy 1, boy 2, or boy 2, boy 1. So each of these 9 factorial ways are still going to have 2 exact arrangements depending on which boy sits where. Correct? So that is why the total number of options is going to be, total number of choices is going to be 9 factorial into 2. 3 particular girls sit together. Similar approach. We have these 3 girls sitting together and 5 boys, 1, 2, 3, 4, 5. How many units we have? 1, 2, 3. These will act as 1 unit, right? So this is 1, 2, 3, 4, 5, 6, 7, 8. We have 8 units. In 8 factorial ways we can arrange them. And now we have to worry about arrangements of these 3 girls among themselves, right? So 3 girls among themselves can be arranged in 3 factorial ways. Correct? So we'll just multiply this by 3 factorial ways, because this 3 factorial ways is independent of this 8 factorial. 2 particular girls never sit together. Okay, this is interesting. 2 particular girls never sit together. So another way to look at it is, we look at total number of options of sitting all these boys and girls together with no restriction, and from there we'll subtract the number of options where two girls sit together. You understand? So what I'm saying is I'm going to look at all options minus the options where two girls are together. So that will give me total number of options in which two particular girls are never together. Right? So how is that going to be? So that is going to be like this. How many options we have total? Total we have 10 factorial options, right? Out of them, I am subtracting the number of options where two girls are sitting together, right? If two girls are sitting together, it is the same problem as two particular boys sitting together. So two girls are sitting together now. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. These two girls are sitting together. How many units I have to arrange? I have to arrange 1, 2, 3, 4, 5, 6, 7, 8, 9. I have to arrange 9 units. This is minus. So 9 factorial ways I can arrange. And this particular unit, which is a composite unit, can be arranged in 2 or 2 factorial ways. So this is going to be my answer. All options minus the options in which girls are together. I'll just write it here, all the answers, so you can check them. This is 8 factorial into 3 factorial, and this is 10 minus 9 factorial into 2. All boys sit together and all girls sit together. Good. So it's all going to all boys together. It's going to be either B B B B B like this, B B B B B, and G G G G G, or it's going to be G, all girls sitting together first and then boys sitting together. So there are two ways in which it can happen, depending on whether boys sit together or girls boys sit first or girls sit first. And then now I'm worried about the arrangement within each group. How many ways can 5 boys sit together? They can sit together in 5 factorial ways. How many ways girls can sit together? They can sit together in 5 factorial ways. So the total number of options is going to be 2 into 5 factorial into 5 factorial. No two girls sit together and no two boys sit together. So no two girls sit together and no two boys sit together mean that they are going to sit alternate. So it's going to be B, G, B, G, B, G, B, G, B, G, or it's going to be G, B, G, B, G, B, G, B, G, B, like that. Correct? So again, there are going to be two ways, where depending on whether boy sits first or girl sits first. So it's going to be 2 multiplied by. Now let's look at only this. These boys are either sitting, I'm only worried about boys now. These boys are either sitting in odd number chairs or even number chairs, right? So I'm only worried about the arrangement among boys, which can happen in 5 factorial ways. Here again I am only worried about arrangement of girls, which can happen in 5 factorial ways. And this 2 is there because the whole arrangement can start with a boy or start with a girl. So here no two girls sit together and no two boys sit together. It's going to lead to 2 into 5 factorial into 5 factorial ways. Right? Let's look at this one. No two girls sit together. No two girls sit together. So that means there is no restriction on boys. Right? Now you will see that no two girls sit together. It appears that it is same as no two girls sit together and no two boys sit together, but that is different, because consider this possibility: no two girls sit together, so that means there is at least one boy between every two girls, right? Now that means we'll have 4 boys, but 5th boy can be sitting here, or it could be sitting here, or it could be sitting here, or it could be sitting here, or here, or here, anywhere basically, right? So that means there are more number of possibilities. This no two girls sit together, one instance of that will be no two girls sit together and no two boys sit together. But there are also going to be other cases where boys are sitting together but still girls are not sitting together. That means this answer is not exactly same, this arrangement is not same as this arrangement. This is very no, general case. So how do we go about it? What we do is, we will only worry about boys now, because there is no restriction on boys, right? So we'll make the boys sit first, and then we'll see in how many ways girls can sit. So no restriction on boys. So I say, boys, you just go and sit yourselves, and just make sure that there is at least one chair in the middle. Okay. Now how many ways can girls sit now? Girls can sit here, here. There is one chair in between every boy. Here, here, here. Or there can also be one chair here. Now let's look at it. Let's count the number of chairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 chairs. So what I do is, I give them 11 chairs and make boys sit like this. I give option to girls to sit in any of these chairs, which will basically ensure that no girls are sitting together. And there will be one empty chair. I'll just take it out. Correct? So how is that going to be? Now girls have options of sitting from 1, 2, 3, 4, 5, 6 places. Correct? So it's they are going to, and we are worried about the order. So it's going to be 6 P5, and boys can sit among themselves in 5 factorial ways. So the answer here, no two girls sit together, is 6 P5 into 5 factorial. There will be one extra chair here. Let's say this chair, if no girls sit here, I'm just going to remove that chair. Okay. Now last problem, another girl is added to the group, and now no two boys sit together. Okay, let's look at this now. I suggest that you pause the video again and try to solve this. Okay, so now how many girls we have? We have 5 boys and 6 girls. Here we have 5 boys and 6 girls, right? Another girl is added to the group, and no boys sit together. That means there is no restriction on girls. So I have I need 11 chairs, but I give 12 chairs to girls first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I say, girls, go ahead and sit on these 12 chairs. No, such that you have one chair in between. So all the girls sit like this. 1, 2, 3, 4, 5, 6. Okay. And how many empty chairs there are now? 1, 2, 3, 1, 2, 3, 4, 5, 6. There can also be a chair here, 7. Right? So there are going to be 7 chairs on which 5 girls will sit. There will be 2 empty chairs. I'll just take them out. Correct? So it's going to be, girls sit among themselves in 6 factorial ways. Out of those 6, you have 7 empty chairs for boys, is 7, and boys sit in those 7 chairs in 7 P5 ways. So the answer here is 6 factorial into 7 P5. I recommend you pause the video and look at all these problems again. You can go through the video for any specific explanation. Let's look at this problem. Please pause the video and give it a try. Okay, in how many ways can a committee of 5 people be made from a pool of 5 boys and 6 girls? Now we are interested only in selecting a committee, so that means a combination problem. Okay, there is no restriction. There is no restriction. That means I have 11 people to choose from, and I need to choose 5 of them. So the answer here is 11C5. A team must have 2 boys and 3 girls. So total I have 5 boys, I have 6 girls. The team needs 2 boys and 3 girls. That means I'll have to select them independently, right? So what do? I need to select 5. From 5 boys I need to select 2, and from 6 girls I need to select 3. So answer here is 5C2, 6C3. the team must have at least one boy. Now whenever you hear this term at least one, there is a trick to go about these problems. When you say at least one, it means all options minus the one in which there is one boy, or sorry, all options minus the one in which there is no boy, right? So the remaining options will always have at least one boy, right? So how many all options we have? We have 11C5 as all options. From these many options, now I am eliminating all the options in which there is no boy. How many ways can we have no boy? That means in how many ways can I have only girls? When I am having only girls, I am only selecting all the 5 members from this group. So that means only girls is going to be equal to no boy is equal to only girls is equal to 6C5, right? I am only selecting from this group. So those many I will eliminate from all options, and these are going to be the number of options in which I will have at least one boy. The team must have at most 4 boys. Okay, so at most 4 boys means all options minus the options in which there are more than 4 boys. Correct? So more than 4 boys means how many? More than 4 boys means 5 boys, because there are only 5 boys here. That means there is going to be one option wherein all 5 boys are selected as the committee member. So this answer here will be all options 11C5 minus 5 case of 5 boys selected from 5 boys, 5C5. A particular girl is always selected. So particular girl is always selected. All I have to worry about is filling up the remaining 4 seats, right? And how many people I have? Overall I have 11 people, but one girl is already selected. So that means I have only 10 people to choose from for the remaining 4 seats. So answer is going to be 10C4. Two particular boys are never selected. Okay, these guys are never selected, so I really don't have to worry about it. That means what I have to do is, I had 11 people earlier, now I have only 9 people. I have to worry only about them, and I need to select 5 people from them. So the answer is going to be 9C5. Let's look at these now. Jack, who is one of the boys, is selected. If Jack is selected, then his sister Lily is also selected. Okay, so there are 2 cases here. That Jack is selected, that means Lily is selected, and Jack is not selected, right? And we don't know anything about Lily. It does not say that if Jack is not selected, Lily is not selected. So we don't really know anything about Lily if Jack is not selected. Correct? So let's say consider these cases. Now we'll see that these are cases that are related to each other, in the sense that either this case will happen, or this case will happen, right? So whenever you have an or kind of a situation, whereas something this or this, you add the number of combinations. Whenever you have an and kind of situation, that means I need, like for example here, the team must have 2 boys and 3 girls, right? This is an and, so you multiply. See here we are doing multiplication, so we are multiplying the number of cases. Just remember this: whenever you have and, you multiply; whenever you have or, you add them. So here we are going to calculate number of cases here independently, we're just going to add them. So let's look at the first one. Jack is selected, and because of that Lily is also selected. So that means 2 people are already selected. I need to worry about filling 3 seats from remaining 9 people. So this is going to be 9C3, correct? Why 9 people? Because 2 people are already here selected. I am only worried about out of those 11 people, 2 are selected, so I am only left with 9 people, and 2 people are already selected, so I have only 3 seats, so I am only worried about picking 3 students. So in this case Jack is not selected, but Lily may get selected or even may not get selected. That doesn't really have any bearing. So Jack is not selected, so I have 10 people to choose from, and I need to select 5 people. Jack is not selected, so that means he is not occupied any space on the committee. I still have 5 people to choose. So this is going to be an OR case, so we just add those number of cases. Let's look at this one. Either Jack or Lily both are selected or both are not selected. So this is again an OR type of situation. If Jack and Lily both are selected, that means Jack is there on the committee, Lily is there on the committee. Or Jack and Lily both are not selected. That means Jack is also not selected, Lily are also not selected. So if Jack and Lily both are selected, I have 3 seats to fill out of 9 people. Correct? If Jack is not selected, Lily is not selected, that means I still have 9 people, but I have to select 5 people out of that. So it is going to be 9C3 plus 9C5. So I recommend you pause the video and go through all these problems again. You can refer back to the video for any specific explanation. Let's move to this problem. Please give it a try. In how many ways can 10 people be seated along a circular table? Okay, so this is a circular table. What if 3 particular people of 10 always sit together? Okay, let's look at this first. In how many ways? Let's forget about any restriction. Let's just figure out how many ways can 10 people be seated along a circular table. So when we are making people sit in rows, okay, so how many ways can people be sitting in a row? This is going to be 10 factorial ways, right? Correct. Now look at this. We have circular table, 10 chairs, correct? We have A, B, C, A, B, C, D, E, F, like that. Now every individual says, for a particular arrangement, every individual says, no, I'm going to move 1 chair to the left. So what you end up getting is A sitting here, B sitting here, C sitting here, D sitting here, like that. Correct? But it's a circular arrangement. So with respect to A, the arrangement is the same, right? And we are not giving any particular number to a chair, that this is first chair, this is second chair. If that was the case, then it would be, you would have to worry about the order. Here we are worried about the relative order. So we are always worried about the order with respect to one individual, right? So here in this case, what we do is we say, okay, let the first guy sit anywhere. Okay, let A sit anywhere, and now with respect to that position of A, I am going to look at all the possible combinations for other guys, right? So that means the next guy has 9 ways to choose from, 9 chairs to choose from. The other guy has 8 chairs to choose from. The third person has 7 chairs to choose from. So that means we are going to have 9 factorial ways of making this seating arrangement in a circular fashion. Once again, what we do is we look at number of combinations or number of arrangements from one particular person's point of view. So we assume that he is sitting at a particular place. We refer to that chair as the origin, let's say, and from with respect to that origin or with respect to that fixed position, we are looking at all the combinations, right? Now also consider this. Let's say we have this A, B, C, D like this, okay, and we number those chairs, okay. So it's going to be 1, 2, 3, 4 like that till 10, okay. Now this is, we move this combination 1 to the left, 1 to the left, 1 to the left, like that, and this guy, last guy, comes and sits in the first chair. Now if we are making them look, if you are considering this problem from sitting in a row perspective, then that is going to be a different arrangement, right? But with a chair perspective, sitting in a circular fashion perspective, it's going to be the same arrangement. And there are going to be 10 such arrangements, because in 10 different places we can rotate this arrangement. So that means row arrangements, number of rows divided by 10 is going to be the number of arrangements in circle. Correct? So it's the same thing. Row, how many arrangements we have for row? We have 10 factorial divided by 10, we get 9 factorial. So that is why the trick here is that whenever you are worried about 10 people, or rather whenever you are worried about people sitting in a circular fashion, we subtract 1 from here and we are only worried about n minus 1 people, and n minus 1 factorial is the number of ways in which they can sit around a circular table. This is with no restriction. Now let's look at some restrictions. What if 3 particular people of 10 always sit together? Same thing, 3 people are always going to sit together. That means let's say A, B, C, D, E, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So they are these 3 people always sit together. So how many units I have to fix? I have to fix 1, 2, 3, 4, 5, 6, 7, 8. I have to fix only 8 units. In 8 units in circular fashion, so I can do that in 7 factorial ways. And in how many ways can these people sit among themselves? They can sit among themselves in 3 factorial ways. So answer here is 7 factorial into 3 factorial. What if 2 of the 10 never sit together? 2 of the 10 never sit together means all the possible combinations minus the combinations in which they sit together. Correct? So what are all the combinations? All the combinations is 9 factorial. And if 2 of them are sitting together, what is number of combinations in which they sit together? If they are sitting together, let's see, look at it this way. First guy, second guy, third, fourth, fifth, sixth, 7, 8, 9, 10. Now we need to subtract number of combinations when they are sitting together. Let's say they are sitting together. So how many units I have? Now I have 9 units. That is going to be arranged in 8 factorial ways. And relative position of these two, that is going to be another 2 factorial ways. So these are the number of ways in which they sit together. But I want they never to sit together. That means I'll subtract these many cases from all cases. All cases is 9 factorial minus these many cases, 8 factorial by 2 factorial. So this is the number of cases in which 2 of the 10 people never sit together. What if there are 10, what if these are 5 couples and each couple sits together? Pretty straightforward. So I have 5 couples, 1, 2, 3, 4, 5. All the couples are sitting together, so that means this is going to be the order like that. Correct? So how many units of groups I have? I have 5 groups. So the 5 groups in circular fashion can be arranged in 4 factorial ways, and each group is going to have 2 ways of sitting. So depending on whether the husband sits here or the husband sits here, we are going to have 2 different ways here, 2 different ways here, 2 different ways here, 2 different ways here, 2 different ways. So then it's going to be 2 raised to 5. What if the chairs are numbered? Pretty interesting. If the chairs are numbered, the problem will reduce down to making them sit in a row, in the sense that making them sit in numbered chairs. It is a different fact that the chairs have been arranged in a circular fashion, but it doesn't matter, because circular fashion, the whole assumption is that there are no numbers to the chair. There is no absolute position for any particular situation. It's all relative. But when they are numbered, there is a reference system for us, the number system of chairs, and that is why the problem reduces down to it being a problem of rows, in which case we are going to have 10 factorial ways of the people to sit. Let's look at this problem. Please give it a try. In how many ways can 5 red balls, 4 green balls and 3 black balls be arranged in a row? Okay, so how many balls we have? 5 plus 4 plus 3. right? This is 5 plus 4 plus 3, so you have 12 total balls. So number of arrangements is going to be 12 factorial, right? Correct. But now look at it. Let's say one of these arrangements is this 5 red balls, so it's 1 2 3 4 5, 4 green balls. This is, let's say, one of the arrangement, right? Now here when I'm talking about 12 factorial, I'm considering all these items as individual items. That means I'm worried about the order of which exact ball sits where. But in this kind of arrangement, it really doesn't matter whether it is R1 coming first, R1, R2, R3, R4, R5 like this, or it could also be R1, R2, R3, R4, R5 like this. This 12 factorial is including all such cases wherein it is treating every red individual ball as a different entity. But we don't need to do that, because all we are worried about, there is no distinction between any of the red balls. All we are worried about is a combination of overall 12 balls, and I'm going to treat all these red balls as same. So that means these many cases are extra included in this, and I'll have to divide this 12 factorial by these many cases. And how many such cases are going to be? There are 5 red balls, so there are going to be 5 factorial ways that are included in this 12 factorial that I don't need. Similarly here 4 factorial ways I don't need, here 3 factorial ways I don't need. So I just divide it by that, 5 factorial, 4 factorial, 3 factorial. Correct? Also another trick that we have seen in one of the earlier slide is all status factorial by status 1 factorial, status 2 factorial, status 3 factorial. So here what we'll say is all status factorial is 12 factorial divided by, this is one of the combinations, how many R's we have? I have 5 R's. How many greens we have? I have 4 greens. How many blacks I have? I have 3 blacks. So if you apply that approach, you will get the same answer. If you understand the logic why we are dividing by 5 factorial, well and good. If you don't understand it, just remember this formula: all status factorial divided by 5 factorial, status 1 factorial by status 2 factorial by status 3 factorial. Let's look at this problem. In how many ways can letters of the word Mississippi be arranged to form new words with or without meaning? Okay, so we'll see that how many letters we have: 1 2 3 4 5 6 7 8 9 10 11. 11 factorial ways in which you can do it. But again, last the similar problem, how many m's we have? We have 1 m. How many i's we have? We have 1 2 3 4 i's. How many s we have? 1 2 3 4 ss we have 4, and we have 2 p's. Correct? So we are because there is not going to be any difference between any of these i's or any of these ss, we are going to have to divide it by that, because they are all of the same status. So 11 factorial divided by 1 factorial for m, 4 factorial for I, 2 factorial for p, and 4 factorial for s. Whatever that number is going to be our answer, right? But here another trick is, it is asking us for new words. So how many new words? All these words is all these combinations, one of that combination is going to be Mississippi, but we are only worried about new words, so we'll have to subtract 1 from this. So 4 factorial, 2 factorial, 4 factorial minus 1. This is the answer. So with that, we come to the end of this session. I thank you for watching the video, and I look forward to meeting you in the next class. Thank you.